All right, part 2 of special substitutions for integration. We get into the fun with trig now. So we have the integral of sine cubed dx. In the previous video, we saw that doing these substitutions gave us a polynomial that we could integrate fairly easily. Well, I guess not a polynomial, but a function that we can integrate very easily with power rule and things like that. And the same thing is going to happen with these substitutions for trigonometry. If we see in an equation that we're integrating sine or cosine functions to an odd power, here's what we do. We're going to rewrite it as 1 less of an exponent times that trig function again. So I've just broken one of the trig functions off. And what does that do for us? Well, that allows us to use the Pythagorean identity. So this becomes 1 minus cosine squared x times sine x dx. And we can distribute. And you might be going, well, this seems like it's making it worse because now we have sines and cosines in the problem, but that's actually a good thing if you think about U substitutions. So we get sine x minus cosine squared x sine x. And antiderivative of sine is, well, that's pretty darn easy. That would be negative cosine x minus the integral cosine squared x sine x dx. And here we're going to use a substitution. I'm going to let u equal cosine x. So du is going to be negative sine x dx. So we need a negative and a negative outside to balance out, which makes out here a positive. And we have our sine x dx right there. So we have negative cosine x plus the integral u squared du. And look at that little beauty. That's very manageable. We can hang with that. Cosine x plus 1/3 u cubed plus c. Well, what was u? U was cosine. So we can clean this up and rearrange it to become 1/3 cosine cubed x minus cosine x plus c. And there we go. We're done. Isn't that nice? So now we have sine to the 4th x. So we have sine x to the 4th power. Even power of a trig function. If we have sine or cosine to an even power, what we're going to use to make this turn into something very nice and glorious that we can deal with is the double angle identity for cosine. And the whole reason we use that is because the double angle for cosine is equal to something involving sines and cosines squared, even powers. So let's start with that. Let's take the cosine 2x equals, we'll use the one with the sine squared in it because we have sine here. So it says 1 minus 2 sine squared x. We can rearrange this to see that sine squared x is equal to 1 minus cosine 2x over 2. So back here with our integral, we have that quantity squared. All right. Well, the whole reason we're doing this is because sines and cosines, regular boring sines and cosines to the 1st power, are easy to anti-differentiate. But as long as they're squared, we got to do work with them and make some substitutions, or cubed. And that's what these examples are all about. So we can expand this. Numerator becomes 1 minus 2 cosine 2x plus cosine squared 2x, and this is all over 4 dx. So we have 1/4, easy to anti-differentiate, minus 1/2 cosine 2x, again, easy to differentiate, plus 1/4 cosine squared 2x dx. And that last part, not quite so easy to differentiate because it's still a trig function squared. So what do we do? What strategy did we use up here at the beginning? Well, we used double angle for cosine. Double angle for cosine involving cosine squared says 2 cosine squared of x minus 1. But we don't have cosine squared x, we have cosine squared 2x. So over here on the left, it's not cosine 2x, it's cosine 4x. And we can rearrange this to see that cosine squared 2x is equal to cosine 4x plus 1 over 2. These two right here, muy importante. Very important to be able to work with and understand where they're coming from and substitute into anti-differentiation. So here we go. We have integral 1/4 minus 1/2 cosine 2x plus 1/4, I guess it would become 1/8 times cosine 4x plus 1 dx. And before I take any antiderivatives at all, I'm going to expand just a itty bit further. And 1/4 plus 1/8, that's 3/8. So let's just combine some like terms. And these three terms are all things that we can find the antiderivative of. We have 3/8 x minus 1/2 times 1/2 cosine 2x, so 1/4 sine 2x. We should be very comfortable taking the antiderivative when we have a linear expression inside of a trig function, or any other function for that matter, plus 1 over 32 sine 4x plus c. And there is our antiderivative, ladies and gentlemen. We'll look at one more example before we get on to another great and wonderful idea with integrals and anti-differentiation. And this one is even bigger and beefier and crazier fun than the last. So what do we have here? We've got an even trig function. We've got an odd trig function. Oh boy. Well, let's start with the odd trig function. Sine to the 4th x cosine x to the 6th times cosine x dx. And what do we do with that even trig function? With that cosine to the 6th power now? Well, remember that's cosine squared x cubed. When we're working with these odd trig functions, we're using a Pythagorean identity substitution. So we have sine to the 4th x times 1 minus sine squared x cubed cosine x dx. Oh my goodness, my head hurts just looking at this. But guys, relax. Something nice actually happens here. We're going to follow the same strategy as when we took the antiderivative of sine cubed. We'll let I'm going to let u equal sine x. I shouldn't say the same thing because I'm not going to distribute, because expanding this out right now, the 1 minus sine squared x cubed, that's going to get really big. But I can let u equal sine of x right now. Du equals cosine x dx. Well, isn't that nice? There's cosine x dx. So this integral becomes u to the fourth times 1 minus u squared cubed du. Well, that's something that we can work with. We can use the binomial expansion. 1 minus 3u squared plus 3u to the fourth minus u to the sixth du. Now we can distribute. And those are all terms we can take the antiderivative of. So we have 1/5 u to the fifth, and u was sine of x, minus 3/7 u to the seventh, so 3/7 sine x to the seventh power, plus 1/9 sine x to the ninth power. Okay, so it would become, we had 3 times 1/9, so 1/3 sine to the ninth, minus 1/11 sine x to the 11th power plus c. And there we go, third example. That one looked the biggest and the scariest, but it was actually very nice and cuddly if you think about it. So in the next video, in video 3 of this series, we're going to take expressions that don't have trig functions, and we're going to substitute them in, and some very nice things are going to happen.